The broadcast is now starting. All attendees are in listen-only mode.
Good evening all, and welcome to the January PWI Glasgow Section meeting. A little reminder about some domestic arrangements. The meeting tonight will be recorded, all cameras off, and the audience will be muted during the presentation. There'll be time to speak later. During the presentation though, please raise any questions or make comments via the dashboard questions pop-up. You should be able to see that little thing that says questions. You can type questions in there, and I'll take those questions after the main presentation. Okay, some section news and apologies. As you'll see there, the 2021 section meetings, there's no change. We'll be carrying on the third Wednesday every month, as we are on a webinar until current restrictions are lifted by some shape or form. And then we will eventually return to face-to-face meetings in WSP's Queen Street conference room as before, and we'll continue to do that as face-to-face and recorded webinars. A little bit of section news involving Edinburgh. The Glasgow section was represented at the Edinburgh section meeting quiz, and I regret to say came miserably third in that quiz. The winner was Gash McRae. For those you know, Gash McRae from Dalgety Bay was a worthy winner. Okay, just bear with me a moment. Tonight's presenter, Killian Farrell, is a senior infrastructure engineer with Arcadis. A little bit about Killian for those who don't know him. After he graduated as a civil engineer in Ireland in 2009, Killian completed his master's degree, with honours of course, in design and digital media at Edinburgh University. Began his engineering career after university in the nuclear industry, almost 10 years ago now, working with EDF Energy in Paris, before moving back to the UK in 2015 to take up a similar nuclear industry position as a civil engineer with AMEC Forster Wheeler, and then C2HM Hill in Glasgow. Killian moved to his current role as Senior Infrastructure Engineer in Arcadis in April 2018, and his paper tonight is Digital Signal Sighting for Cadder HST Depot. I'm going to now change the presenters to Killian, and you may have seen shots of his presentation. One moment.
Hello, can you hear me?
Yes, that's fine, Killian, and I'll just start the recording now.
I'm assuming you can see my presentation as well.
Yes.
Right, so thanks for the introduction. Again, my name is Killian Farrell, and this presentation is on the work we did in Cadder for signal sighting. The presentation itself is split up into 3 different sections. First of all, there's the digital technologies. So this is to give some context and talk about the different technologies that we've used within the Rail System Alliance Scotland and Arcadis over the last couple of years. And then I'll talk about signal sighting and then go into detail into the example, which is the Cadder signal sighting and what we actually did there. So in terms of digital technologies, so data collection tools are getting increasingly better in terms of cost, ease of use, and quality of data collected from site. Nowadays, you can go out on site and capture a whole lot of information really easily compared to previous years. Traditional data capture technology includes, traditional terrestrial laser scanning, where with a static laser scanner, you can go and capture a point cloud or a LiDAR scan of an entire site. Nowadays, that's become more readily available, and it's been miniaturized in the form of mobile laser scanning. So here's a couple of photos of me doing some bridge inspections in Edinburgh with the mobile laser scanner. This type of information allows us to do all sorts of wonderful drawings, models, and analysis. Something that's really, really useful for a relative low cost. So some of the examples you see here are bridges that we've scanned and done, produced a whole series of drawings. This is mostly work that I did when I was part of a bridges team. So some of the stuff that we can also do is analysis. So in this example, we scanned 60 bridges in Edinburgh over 5 days, and we produced, we developed some processes to do some semi-automated analysis of those bridges to be able to determine minimum headroom clearance for vehicles under there, essentially to ensure that all signage was accurate and to make sure that vehicles wouldn't strike the bridge. This is something that wouldn't have been possible even just a few years ago, seeing as the actual method that this was being done by the council up until recently was rolling police blockades, where engineers would go out with the disto and look at the bridge and try and determine what they assumed was the lowest point on the bridge, measure it with the disto, and then that was the height that was marked on the signage. Whereas the process that we did, we've actually done a full scan of the entire bridge and then done analysis that allows us to accurately determine where that pinch point is and what that clearance of the actual bridge is. And some of the instances, as you can see in this bridge, sometimes the bridges aren't actually, it's not very obvious where that pinch point might be. So the second form, so that's the kind of a point about laser scanning. Again, there's the static ones, and then there's the mobile laser scanning. Another technology which has existed for quite a while, but it's been improved dramatically over the last 10-15 years, is photogrammetry. And effectively, photogrammetry is creating 3D models based off of photographs or videos. So the 4 examples you can see on screen there, those are 3D models that I produced myself using my smartphone. So effectively collecting the information and scanning the information with my smartphone, and then post-processing it on a laptop afterwards. So you can see that the level of detail and the accuracy is actually quite high, and when it's used in the right context, it's quite a powerful tool. Here's just a quick video which kind of summarizes that, where I'm walking around a subject that I wanted to capture. Recorded a video in this instance. Actually, for the processing, I actually used the camera and used still images, but that can then be used to create photorealistic 3D models, which, again, if you do it right and if you know how to do it, you can actually get something that's measurable and it's to scale, and that allows you to actually take dimensions and to do some analysis work on that as well. Something that's really useful to do for structural inspections and defect inspections. Obviously, you can do that at various different scales depending on you know, what type of method that you capture and what the subject is that you're trying to capture. I've got an example here of a full bridge that I scanned. It was actually the day that, or the morning that we went into lockdown, where we were doing an inspection, and we had a series of inspections planned for this bridge, but we were only able to do it once because it happened to be the day of the lockdown. So we ended up doing a full scan like this, and this allows us to effectively revisit the site afterwards without having to actually visit in person. You can just get the 3D model and view it that way. So that's photogrammetry. Again, here's some examples of some that were created in some tunnel projects. So one of the big buzzwords of the last few years is drones. Drones are effectively a means of carrying the scanning equipment. So you've got drones that can do LiDAR surveys, or drones that can do photogrammetry, and effectively it's the same process as I mentioned in the 2 examples above. It's just that the camera is being flown around the site, so it can cover a much wider area and capture a lot bigger site of a lot bigger in size. Here's an example of the Carstairs Junction that we scanned, and this is one from Cadder, which you will see later on in the presentation. So for this project, we've actually scanned the entire site, and that allows us to use this information for a whole raft of different reasons in the project, from visualization to minimize site revisit to driver training. You can imagine, instead of going out to site and revisiting it, you can actually just virtually visit it online, which is quite a powerful tool. Minimizes the risk on site and improves safety and all that. So that's the different technologies we're using on site. We've used a number of these in Cadder. There was a link between them. But how do we actually use the technology once once we're back in the office and we want to use this information? What's the things that we can do with it? So a lot of things we do is standard visualization, but in terms of the actual practical applications, we've developed bespoke solutions for clients. So some of the more innovative examples that we have is an inspection tool that we developed, which allows us to effectively load up photogrammetry models and combine them with LiDAR surveys into an environment that's free of CAD tools or licenses or anything like that, and allows the client access to all the information that was captured on site in a simple and easy to use color-coded application. I'm sure everyone at this stage has probably heard about virtual reality and augmented reality. This technology allows the users to effectively put on a virtual reality headset on their face and visit a site and experience situations and scenarios within the safety of their offices or their homes, as is the current situation. And this really is a powerful tool when used correctly. It can bring users to site without the need to actually do it. And we're using this in a number of different training situations, like in the example that you've seen above. This is a piece of work that we did for the Rail System Alliance Scotland, where we were essentially doing different simulations of the maneuver of this particular crane. The augmented reality piece. This is a short example of the same project, but it's allowed us to essentially through a smartphone, you can load up a series of different 3D models and view them on your smartphone in the context of the real world. It was, there's different uses and applications, but this is just one example that we put together. It allows us to just create an interactive and slightly different application that allows users to view the information in a slightly different way, and we found it to be useful for different use cases. So 3D printing, this is one that not quite related to Cadder, but it's something that we're doing increasingly at the moment in terms of the digital technologies. Producing actual real-world physical models sometimes is quite a powerful tool to convey different messages across to different clients, and we've found that it's actually been really useful. Some of the instances that we've used are situations that you probably wouldn't think of straight away. One of them that we did recently was for a bridge project in Edinburgh, where the City of Edinburgh Council had produced a fancy 3D model and a virtual reality experience to showcase their designs of the new bridge to the public. What they didn't realize is that one person that was super eager to check out this model was actually a blind individual. They understood the 3D model was going to be a physical 3D model and not an actual virtual model. So what we ended up working with the council to produce a 3D print, kind of a scaled 3D model of the bridge. We took it a step further and we actually broke down the model into individual parts, and that allowed us to do a kind of a construction sequence building of the 3D model in different steps to explain to the individual that these are the different steps. This is essentially a kind of a 4D construction sequence of the bridge, doing the earthworks, putting in the walls and putting in the deck and stuff like that. And that was a really useful use case of the technology. So it's a good example just to show that there's often technologies out there that you might not think of for different solutions. We did some work for the NHS on one of the Nightingale hospitals as well, where we printed scale models of some of the hospitals for logistic reasons. One of the interesting examples, which we're going to be seeing increasingly in the UK over the next couple of years, is the image recognition technology. At the moment, Arcadis are working in the US and in the Netherlands. We've created applications that allow us to mount cameras to the front of trains, simple cameras such as something as simple as a GoPro, and allows us to use this tool, which was developed internally, and allows us to actually run through and analyze all of the imagery that will automatically detect different assets in terms of their location, their condition, and can then display that information on a GIS on a GIS tool. And that's something that's really powerful, because the more sophisticated these get, the more practical applications that come with that in terms of predictive maintenance and things like that. You can actually detect the condition of different assets over time based on the images, and you can then start doing some predictive maintenance and modeling from that. So that's just a look at the different technologies that we've been using over the last couple of years, or the last number of years. Signal sighting. So I'm assuming here, most people know what signal sighting is. So I've got a couple of slides just kind of showing it and explaining it, just in case anyone doesn't necessarily understand. But for all intents and purposes, a signal is effectively a traffic light for trains, and signal sighting is the process of ensuring that signals are visible to drivers in order to allow them enough time to observe, think, and act on them. It's crucial for maintaining the safe separation of trains. So why is it so important? Well, a report found that in the Ladbroke Grove crash, or the Paddington rail crash, a report found that poor signal sighting was one of the leading causes of the accident. And in this example, 31 people lost their lives and 417 people were injured. So it's quite important that signal sighting is done, and that it's done correctly. So obviously this was quite a bad example, or quite a bad situation. So the current design process hasn't changed a lot in recent decades. So on the left is a recent photo of someone doing some signal sighting on site, and on the right hand side, someone doing it a little bit a while ago, probably a number of decades ago. So you can see that there's not a whole lot has been done, has changed. So obviously processes and that have changed, but the overall the design process hasn't changed substantially. So at the moment, the signals are designed in 2D straight line drawings like the one you're seeing here. They don't factor in topography, track curvature, or local features such as bridges and structures. The proposed locations are established here, and then they're investigated on site to ensure that that they're in a correct location. This leads to an iterative design process where the design is done in an office. Someone goes out on site to check it, which isn't the most efficient way of doing it. As you can see here in an example, you've got a train driving, and then someone's erecting a kind of proposed signal location. So this can lead to this can produce results of varying quality. So digital solutions do exist. There's a whole raft of different kind of options out there. Some of them are offered by certain companies that offer it as a service. Some of them are kind of software based. But for the Rail System Alliance Scotland, for Cadder, we decided that we would try and develop something bespoke ourselves. With Cadder, we're actually doing quite a bit of visualization work, and we're designing custom tools anyway. So this was an example of one that we decided to do ourselves. We've got great experience in developing these tools and producing high quality visualizations. So it kind of made sense that for this particular example, we can actually just develop our own bespoke solution for doing the signal sighting. And with that, I'm going to change to a live demo of the software. Fingers crossed it goes smoothly. So you should be seeing here is a 3D model of Cadder. What you're seeing here in the distance is the actual 3D model of the aerial survey that was captured on site. So you can see the existing piece of track, which is about 3 kilometers long. What you're seeing on the left-hand side is actually a proposed depot. So there was 2 bits of work that were going on here for the Rail System Alliance Scotland. There's the track renewals on the main line, and then there's a depot that's actually getting constructed here. So part of what we did, because we're going out on site and we're capturing all this information, we're doing the drone surveys, we're doing the visualization, it made sense to develop a signal sighting tool. I think someone's at the door. I don't know if you can hear the dog barking, but ultimately what we have here is a combination of all of these technologies. And what you have is, so the first thing you can see here is the inside of a driver cab. So what we have is we've done an actual photogrammetry survey of the inside of the train, and that allows us to create a realistic environment to do this the signal sighting. We've made it a fully interactive tool. So if I just switch sides, what we've done is you actually have the ability to drive the train. So someone keeps ringing the doorbell, so you just have to excuse me for 2 seconds.
No questions been asked yet, but maybe like me, you're just blown away by all this. What an amazing display of technology. It certainly is, Gus. Absolutely amazing.
Right, apologies for that. I thought I'd locked the wife out and the dog was going mental, but it was just Amazon. So as you can see here, we've got the interactive application that we've developed. This allows us to actually physically drive the train and do a number of different simulations. What we've done is we've developed this tool, and effectively the client or whoever can have a look around and do a full simulation of what it's like to drive into Cadder Depot. So as you can see, so you'll have to bear in mind I'm probably speeding here, driving into the depot at 70 miles an hour, but this because it's a fully interactive tool, you can actually switch between any of the different tracks and do a whole number of different maneuvers. If I just stop this. So without going into too much details as to how we've actually done everything, there's some smart stuff that goes on behind the scenes in terms of how we've developed it. One of the things that we wanted to focus on was automation, and how do we automate this process and make it scalable on any project. One of the things I learned in this project is that a lot of people tend to revise their designs quite extensively, and what we didn't want to do was spend a lot of the time constantly iterating and modeling stuff from scratch. So one of the things we developed, which was essential, was we developed a way of actually automating the process of modeling the tracks themselves. So I'll just show you an example here. What we've done is we can automatically convert a spline design of the center line of a track and convert that directly into a model. If the track people were to revise the design and change any of the parameters, we can automatically generate a brand new mesh that fits the profile of that track with the simple click of a button. And it turned out that was a wise call, because as you guys probably know, the track people like to revise and change their designs constantly, which ultimately saved us quite a bit of time having an automated way of doing that. And same for the signaling. We developed an automated way of importing all the different signals based on a spreadsheet data. So effectively, if you had 10 signals or 1,000 signals, you would just import a spreadsheet and it would automatically populate the entire piece of track with all the signals in the right location, and that would allow the process to be as automated as possible. This example is actually a good example because everything you see on the right hand side here is part of the BIM model that was just imported directly into the software, and we've got some kind of semi-automated processes to speed up how we import these models. So part of the main takeaways here was that we're developing something that's as automated as possible due to the constant changing nature of the actual design of this project. Having the automated process was actually a godsend and allowed us to automate the whole signal sighting process. If there was any changes in the design, they just got automatically updated. One of the things that we also added was the ability to fly around the model itself and have something that would automatically detect the distances between the camera and the signal. So you can see as you fly away, it gives you that distance, so that we were able to identify, at what distances was something obstructed, or at what level did we need to move some stuff around. So we ended up with this really interactive tool that we sat through with the signal sighting committee and went through the whole project and then checked it from a number of different drains, and we were able to change the perspective and have a really interactive tool to do the whole signal sighting process. It actually was well timed in the sense that due to COVID, access to the site was quite limited when we did this back in, it was between I think May and June, and having this was a bit of a godsend because we were able to do effectively most of the work remotely. It's still something that we're doing on site, and we still have to verify it on site. But moving forward, this is something that we can smooth the process and do more of it remotely where possible. So apart from getting interrupted by the dog barking, that's that presentation finished. If anyone has any questions, just please let me know, or feel free to send me an email.
Thanks, Killian. A couple of questions, observations from me first, because for some reason I can't type questions as we go, so I just have to write them old school. A question about the capturing of information first from me. Precision of recording, you mentioned you're capturing it on your own phone, but photogram, that kind of LiDAR non-contact system, what kind of precision does it have?
It completely depends on who's capturing it and how they capture it, and specifically what they're capturing. There's no magic solution that will do everything that you want to do really easily, really cheaply, really quickly, and really accurately. There's always going to be trade-offs between different technologies that you use. Photogrammetry is very good at capturing either wide areas using drones. Effectively, the bigger the model that you're scanning, or the bigger the area that you're capturing, what you're going to see is you're either going to see a trade-off in accuracy or a trade-off in processing time. So if you want something that's very accurate over a wide area, it's going to take a very long time to process it with very powerful machines. Whereas some of the examples that I gave here, which are just small individual 3D models of specific defects, like these ones, these were probably all captured within, took me maybe 30 seconds or 2 minutes to capture the photos of each one of these, and then processed within about an hour. Because I knew because I knew the process and the best practices for it. This is accurate. I've seen studies done where people have it as accurate as laser scans, but it all comes down to the method of how you've captured it and what you've captured. Because if you try and scan the Fourth Rail Bridge, something of that scale, it's going to be a lot harder to do over such a wide area, which is why LiDAR is still really useful, because it is 100% accurate. When you do it properly, it doesn't give us as good a models in terms of the finished quality, but it is more accurate. So it's a bit of a political, or a kind of a politician's answer, because it kind of depends. Your accuracy can go to a few mil, up to a couple of meters if you're scanning from a drone super far away and you're capturing a wide area. But you can get them really accurate, and I have seen studies where on certain sites they've got a comparable between photogrammetry with the smartphone to a laser scanner. But some people's imagination will just extrapolate that and they'll understand that photogrammetry is just as good as laser scanning, which isn't actually true, because they do things slightly differently.
We're just trying to get away from the idea that because it's captured by laser, that it's super accurate. We've had LiDAR plus or minus 25, okay, up to a certain grip stage. You try and do AIP grip 4, LiDAR not good enough. You need plus or minus 5 topple. So
it's one of those things. It depends on how you capture it. Even LiDAR is, as you're aware, is liable to that. If you do, like we use LiDAR for structural monitoring of walls, and that's within 5 or 6 mil or whatever. That's something that's done a certain way. Whereas if you're capturing an absolutely massive site, you mightn't capture it as accurately, because you've got a much wider area to capture. So it completely depends on a number of things. Weather conditions is another one that you can't guarantee. If you capture LiDAR from a drone, that's done using slightly different technology than a kind of a static laser scanner, the way it's kind of tied in all together. So there's different ways of losing accuracy there. So to answer your question, laser scanning and photogrammetry, you can get them very, very, very accurate, but you can also they can also come in not so accurate depending on how they're done.
So if you've got terabytes of room, you're okay. And that was
and a very powerful machine, and you've got
yeah,
time to wait for it to process. Then yes.
that was my next question. You mentioned that in your image recognition, you could offer that to clients, and they could use it to use it for their asset management.
Yes.
But wouldn't that technology require them to have these larger computers? We'll not talk about sizes or anything, but just specialist size computer, not just your run-of-the-mill laptop.
So they wouldn't. So it depends on how you do it. I mean, that's something that's normally offered like as a service. I know the team in the Netherlands, they've developed their own tool. They run the algorithm themselves, and the more intensive part of image recognition is usually the training of the data set in the machine learning aspect, in terms of getting it more and more accurate and building up the training modules. But yeah, that's something that wouldn't be I'm not sure if it would be the client themselves that would do all that. It was something that someone like Arcadis or a product offered by Arcadis would do for them. It wouldn't. I don't think they would actually need the machines themselves. And I know that Network Rail have their own maintenance trains, and they do a whole bunch of different analytics and analysis based on all the information that they gather from that. So that's something they're familiar with. But the solution that we've trialed in the States with CSX and in the Netherlands is based off of a kind of a standard GoPro type camera mounted to the front of a train. I think they do have a kind of a LiDAR unit as well to be able to more accurately geolocate them. But the idea is that you want a kind of a sensible solution that's easy to integrate, not too expensive to integrate, but has a really long-lasting value to it.
Thanks for that. Last thing from me before we go over to the audience questions, and maybe just to defend the corner of the PWI designer. I like the automated process, absolutely fantastic, so useful. But we don't deliberately go out of our way to make iterations of the design. It's normally someone else has prompted that to happen. Okay, on the question. Sorry.
No, I was just going to say that Cadder was, because my background isn't rail. It was funny looking at it from a kind of an outsider's point of view, where the signals were changing this, that, and the other, and then that was causing the track to change, but then that was causing the signal to change. So overall, automation is key. Automation is king, and it's as long as you automate everything, it doesn't really affect you too much. As long as you've done the work and setting it up in a way that it is automated, it kind of makes everything else kind of smooth running.
And between disciplines, communication and sympathy is essential. So the questions we've got written on the web, in the questions box. So the first one from Andy Batters, it says, the Omnicom video database could be used for signal sighting. However, the videos for that have not been refreshed for a number of years. Do you know if that's possible anymore?
I'm not sure, to be honest. I'm not too familiar with that. But in terms of, it depends what's available. I mean, signal sighting, it involves a number of things, including, can you see the signal, but then also the condition of the signal and that. So can you, it depends on a number of things. Technically, you could use, if you had like a GoPro or a video source mounted to the front of the train, you could maybe automate something to do some form of signal sighting. Cadder was a particular example that we all did it in 3D in an automated way because we had the survey taken. But in using existing video, you can do signal sighting based on, can you see the signals that are already there? I guess you'd need to figure out a smart way to integrate, depending on what format the data comes in. How would you integrate brand new designs into an existing video source? It completely depends on what format or how that information comes through. But technically, with all this stuff, anything is possible if you come up with a smart solution. But yeah, I'd have to have more information on what that data would be.
Okay, I'm at loss because I've never actually used Omnicom. From Russell Kimber now, he says, thanks, Killian. Some very impressive high quality output, which makes visualization so much easier. You said its use for signal sighting was relatively bespoke. How did the dinosaurs, that's my word. How did the Signal Sighting Committee receive the use of new technology? And was it completed in parallel with a traditional method with the periscopes or in place of periscopes?
So I can answer part of that question because I know it's an ongoing project, and the actual signal designer and the signal manager isn't actually here on the call. So from my point of view, this was my first time actually working with signal sighting and first time doing the signal sighting committee and going through the whole process. But this actually fell at a time right during some of the toughest COVID lockdown restrictions, where we actually just couldn't go out on site, and there was a bit of an issue there, and we were able to do most of it on remotely. But as I said, for the first time we're doing this, we're not going to just completely. This is something that was done in kind of not in parallel, but in as a kind of a complement to the existing the signal sighting process. So my understanding, I'd have to speak to some of the other guys, but my understanding is that yes, they're still going out on site to verify and do the traditional checks to make sure that everything's okay. But moving forward, if you're trying to make optimizations and if improve efficiencies and safety and all that, it's something that you'd want to do less and less of on site. But because this was our first one, yes, the idea was that they still went out on site to do those verifications. But and I'm hoping what will come out of that is that yes, indeed, everything worked perfectly the first time, because it was we basically simulated the whole thing and visualized the whole thing before going out there, and having the drone survey was kind of essential to that as well. So it really is an accurate representation of the site. So
okay, and next one, Gordon Hope on the signal sighting part again. Could the software automatically produce signal sighting forms?
Yes, is the question. Now it would need a bit more work than what we've produced. We had a scope that we set aside for a certain budget that we said for Cadder we needed to do this, that, and the other. But you can, in theory, get that software then to produce kind of pre-made forms based on a number of different variables. At what distance does it become obstructed by stanchions or gantries or structures or things like that. You can have all of that automated, and ideally if we are planning on taking it to the next step, you can automate that kind of thing. It's not something that's currently in the tool, but it's something that you could in theory do. Yeah.
Okay, that's all the typed questions. I'm going to open the mics now, unmute the audience. So if I unmute all, and if you unmute yourself, if you've muted yourself, then please feel free to raise a question.
Unmuted.
Could somebody say something just to make sure I have unmuted all participants?
Hi there, Tom. It's Jim Watson. Yes, you have unmuted us all. Killian, I've thoroughly enjoyed your presentation tonight, finding it absolutely fascinating, particularly from the point of view of interdisciplinary integration. Have you found in this work at Cadder that there has been some reluctance from their signalling colleagues to accept absolute coordinates rather than schematic drawings with changes and offsets? I know my good friend Harry Archibald is on here tonight, so Harry, don't take offence. It's something I have tried to do in previous projects without success.
I mean, so the team that we've worked with in terms of doing the actual signal design, they were within the Alliance, within the Rail System Alliance Scotland. They were actually involved in this from the start, so they were part of the design team for this. So they embraced the way that we worked in terms of giving us real world coordinates to do that, and it was something that was, because they were working alongside the track guys and the signaling guys, everyone working together. It was something that was relatively easily produced. It's not something that they usually produce, because as you said, having real world coordinates wasn't something that was done normally, but because they were involved in this from the start, it's something that we adapted and basically implemented into the project. So I would say, and I don't know if I was just blessed with a good team that were happy to all collaborate together, but it was actually quite easy implementation for us.
Excellent. Thank you very much, Killian.
No problem.
Any more questions from anybody? Okay. Let me just take you away from that 65 mile an hour went through off Cadder and take you back to my screen. And I'll pass the meeting over to Greg McMillan, who will propose the vote of thanks. Greg, over to you.
Okay, thanks, Tom. So, Cillin, what to say? Well, firstly, just a great presentation. Aside from the videos and the visual side of things, which was excellent, I think you gave a great explanation of the whole process and how it works. And although the topic was Cadder signal sighting, but I think you could have done about 5 presentations on each of the examples you showed us at the start. And you took us through the various methods of data capture, from the laser scanning, the photogrammetry and the drones, etc. And the example of your bridge scanning work in Edinburgh. And the reality capture stuff is really impressive from, what is really just someone with a smartphone. It's amazing how technology has moved on. It doesn't require mega expensive equipment and a 3-person team to go out and do this stuff anymore. Now, obviously, being a fellow colleague, I was aware of your the physical model you printed off for the blind person. I think that's a brilliant example of how technology can be put into a real practical and a really positive use, and it's for everyone. And I'm sure that example alone will be used for future, town hall type community briefings for proposed new works on the railway. So getting on to your signal sighting thing, which is the main topic, it's definitely an overdue upgrade, I would say, to the existing previous methods. As you showed with your photograph of the black and white photo, things hadn't changed too much since then. I'd seen a lot of this before as you were developing it from working on it, but I would say that it still blows me away every time I see it. And not only is the signal sighting part great, but the fact that you've incorporated another key feature of technology, which is automation, by allowing the design models to automatically update your model at the same time. So yeah, it covers everything, including being able to change the simulation for different types of train as well. So really impressive, and I'm sure we'll get you back for future talks on your next latest projects. So also a sign of the times when presenting from home, the dog is barking, but you still didn't let it faze you either. So well done. So I think I'll just finish up by saying thanks, Cillin. Excellent presentation, really impressive and much appreciated.
Thank you. We'll do a little round of applause at this stage. You've got me.
That's all I need.
Okay, I'm going to stop the recording.